Which of these functions from 7 through 12 satisfy the hypotheses of the mean value theorem on the given interval, and which do not? Give your reasons for your answers. So what we'll do, we'll just go through some of these problems. Okay, let's take number 7. Number 7, f of x is continuous from -1 to 8. Okay, and the only problem is when we take the derivative, okay, f prime of x is equal to 2/3 x to the -1/3, which will bring your x in the denominator, and that would mean that it's equal to 2/3 times the cube root of x. And notice that the derivative is not defined when x is equal to 0. So this function is not differentiable at x equal to 0, which is an interior point of this interval. That means we cannot use the mean value theorem because it doesn't satisfy the hypotheses of the mean value theorem on this given interval, -1 through 8. Let's look at number 8. Number 8, we take x equal to f of x equal to x to the 4/5. When you differentiate f of x, we'll have 4/5 times x raised to the, that's 4/5 minus 1, which is -1/5, which is -1/5, and that's just equal to 4/5 times the 5th root of x. Now here, the 5th root of x being in the denominator would mean that it's not differentiable at x equal to 0. But since the function is continuous on the interval from 0 to 1, and it's not differentiable on the end point, but it's differentiable on the interior point from 0 to 1, then number 8, the function number 8, does satisfy the hypotheses of the mean value theorem. Okay, how about number 9? Let's check out number 9. Another way of writing number 9, f of x equal to the square root of x times quantity 1 minus x on the interval from 0 to 1, is just to multiply this through so that we can differentiate it easier. Then another way of writing f of x would be the square root of x minus x squared, or defining it in terms of its power, it would be the quantity x minus x squared raised to 1/2. And this is continuous in the closed interval from 0 to 1. Now what about taking its first derivative? When we take the first derivative, of course, we bring down 1/2, and then this whole quantity raised to the -1/2, and then by chain rule, we have to take the derivative of the inside. When we take the derivative of x minus x squared, it'll be 1 minus 2x. And rewriting this whole thing, we see that the derivative becomes a ratio of 1 minus 2x divided by 2 times square root of x minus x squared. And because this is now in the denominator, the factors x times 1 over x will be 0 when x is 0 and when x is 1. So what is our interval? Well, our interval is from 0 to 1. Since the only time that it's not differentiable is at the end points, then this still satisfies the hypothesis of the mean value theorem. It's continuous on the closed interval 0 to 1, and it is differentiable on the interior, on the open interval from 0 to 1. Let's look at number 10. We've got a piecewise function right here, and if you recall, the limit of sine of x over x as x approaches 0 is 1. But f of 0, as we defined here, f of 0 as defined here, is equal to 0. Since the limit as x approaches 0 is not equal to f of 0, that means f is not continuous at x equal to 0. So already it doesn't satisfy the first condition of the mean value theorem, so we cannot use mean value theorem on the function on number 10. Alright, let's look at number 11. In number 11, there's something here that we have to watch out. It's a piecewise function, although these are both differentiable, both continuous. What we need to watch out now is at where they're partitioned or where they are separated. In other words, f of x is defined as x squared minus x from -2 to -1. And then from -1 to 0, it's defined in this way. So what we will do now is to make sure whether the function is continuous at -1. So what we'll do is look at f of -1. f of -1 is equal to 2. You just plug it in here at plug -1 into x squared minus x, because that's where it's defined. They said that x is equal to -1 here. Now the question is, to the right of -1, in other words, as x approaches -1 from the right, as x approaches -1 from the right, we want to make sure that the limit is equal to 2. Well, since the function is defined as 2x squared minus 3x minus 3 from -1 to 0, so that means we will use this function is where we will plug in the value of -1 to find its limit. So the limit of the function as x approaches -1 from the right is equal to 2 times -1 minus 3 times -1 minus 3, and that is equal to 2. So that means that f is continuous on the whole interval, because we've seen that where there might be a break or a discontinuity, we have checked that indeed they are equal to each other, therefore it's continuous at x equal to -1. So f satisfies the continuity condition on the closed interval -2 to 0. Now the next thing we do is take the derivative of f of x in these two, for these two. And the derivative of f prime of x from -2 to -1 is 2x minus 1. And then we substitute the derivative at -1, and we see that it's equal to -3. Now we take the derivative on the other side on the right side of -1, we differentiate this function, and we see that the derivative is equal to 4x minus 3. Now you plug in -1 into this derivative, and we see that f prime of -1 is equal to -7. What does this tell us? This means that their derivatives are not the same. That means on the left side of -1, this is its derivative. On the right side of -1, this is its derivative. So they should have the same derivative on both sides of -1, which tells us that based on these two things, we conclude that f is not differentiable at x equal to -1. So number 11 does not satisfy the hypothesis for the mean value theorem. Alright, what about number 12? Let's look at number 12. Again, these are two continuous functions, but we just want to make sure at where they're separated or where they're different is when x is equal to 2 is when they will differ. So the question is, are they connected at x equal to 2? So what is f of 2? F of 2, we use the top definition of f of x. So we plug 2 into x and we see that f of 2 is equal to 1. Now we check the limit of the function as x approaches 2 coming from the right. So if it's coming from the right, we have to plug in values, or we have to plug into the second or the bottom definition of f of x. And that is equal to 6 times 2 minus 2 squared minus 7 is equal to 1. So since the limit is equal to f of 2, then we can conclude that f is continuous on the closed interval from 0 to 3. Now, we've satisfied the continuity condition. Our next question is, well, is it differentiable at x equal to 2? Okay, so for the function on the top, we take the derivative, and that's just equal to 2. And then if we take the this derivative, the derivative of the function at the bottom, that means it's equal to 6 minus 2x. Plug in f, evaluate f prime at 2. That's just 6 minus 2 times 2, and it's equal to 2. Since the derivative of f of x to the right, to the left of 2 and to the right of 2 are equal, we can conclude that f is differentiable at x equal to 2. And so it would mean, therefore, that since that is the only critical part that we have to check out, then we can say that f is differentiable on the interval from 0 to 3. So number 12 satisfies the hypotheses of the mean value theorem on the interval from 0 to 3.